So here we are. This is the problem we're doing. A 1200 Newton uniform beam, oh good, they gave us the weight, is supported by a cable as illustrated in figure here, so it's this one here. The boom is pivoted at the bottom, boom there, and a 2000 Newton object hangs from the top, okay. Find the tension of the cable and the components of the reaction force. So that's our hinge force. Okay, so pretty straightforward there. So let's start by drawing our free body diagram. So here's my boom. I'm not going to make it have thickness. That's just annoying. And we know that there's a weight hanging here. I'm just going to call this mass 1. So I'm just going to call that FG1. We know from the center of the boom is going to be FG of the boom. And we know that there's a tension that is pulled off in this direction here. And we know that this angle here is 25 degrees. So I'll say theta t, and I'll just say over here theta t is 25 degrees. We know that the boom angle here also is 65 degrees. Oh, and that's a really nice geometry there because those two are complements of each other. So they're really doing us a favor. But anyway, so let me label some important distances here. I know the entire length of the boom is, oh, they don't give it to us, so I'm just going to call it L, right? That the guy wire there is at 3/4 L, and I know that the boom's weight is going to act at L/2, right? I'm going to put the pivot down there because I'm about to draw my pivot forces and I have no idea what directions are going to go. I'm just assuming that everything's kind of pushing down this, that this is going to be upwards. And since that's acting to the left, that this has got to have something to the right just to balance that out. So, and we're looking for both of those. So there we go. I'm going to pick my axes up to the right counterclockwise, meaning I have to come here and draw in Tx and Ty. And so there I have it. So here I go. Let's construct some equations. Sum of forces in the x is equal to max. Just get this out of the way. Fpx minus Tx is equal to 0. So Fpx is equal to T cosine theta t, right? Which I already know is 25. Good, so once I know T, that's just child's play. Sum of forces in the y is equal to may. So this is going to be Ty plus Fpy minus Fg1 minus Fgb is equal to 0. We're given some numbers here, so I'm just going to put them in the same way that I did before. Let's see what we got here. T sine theta t plus Fpy is equal to, we were told that Fg1, that this was a 2000 Newton object, and the boom itself was 1200 Newtons. I probably should write that here in terms of unknowns, all right? Just so I have my knowns and unknowns there. Okay, great. Now I'm going to leave a little bit of space there because I know I'm going to have to plug into that stuff. And now I'm going to go here and sum of torques about our pivot is equal to 0, right? Or the I alpha, that goes to 0. And let's just actually zero all those out as well. So here we go. So plus Tx, so that's going to be T here. I'm going to actually put in a little bit more than I put in before because I'm actually solving this and I'm not just doing it hypothetically here. So T, actually, let's do positive torque due to Tx, positive torque due to Ty, negative torque due to the beam, and negative torque due to object 1, just so we have a solution pattern set up. So now I will go to parentheses. And I'm going to fill this out as I go along. So Tx, so that's going to be T, and I know this is cosine 25, and then the lever arm distance, right? So I'm going to leave that for now, because that's really what the trick of the problem is figuring out the lever arm distances. Plus Ty, so that's T sine of 25, and then leave space for the lever arm distance, minus the beam, which we know is 1200 newtons, and lever arm distance, and then 2000 newtons, and then lever arm distance, and that's equal to 0. So let's do the lever arm distances now. Tx is a horizontal force, meaning I need this vertical distance right here. And so that's at 3/4 L, right? But not all 3/4 L, it's only the vertical part of it. 3/4 L times sine of 65. And then that makes this 3/4 L, because this is the y component. I want that horizontal distance times cosine 65. Here, 120, or rather 1200, that's here. So it's a vertical force, so I want a horizontal distance. So that's half L cosine 65. And up here, once again, it's a vertical force, I want a horizontal distance. That's L cosine 65. So let's make our lives easy now and cancel out all the L's, which is nice. And then let's just actually do some calculation over here. We'll move all this to the other side. And so when you just put all that to your calculator, you will get the number 1352.4. That's going to be fine. 1352. And over here, let's see what we have. What's common? Oh, well, 3/4 is common to both terms, and t is common to both terms. That's nice. And so what do I have left here? I have cosine of 25 sine of 65 plus sine of 25 cosine of 65. Oh, that's familiar, isn't it? Hopefully you recognize that as sine of a plus b, right? So that is sine of 25 plus 65. Now this, like I said, this is a very cooked problem. It's so nice and easy because that's sine of 90, which is 1. So this entire term goes to 1, right? So therefore, t is just equal to 4/3 of that number. But very common in these angled beam problems, you will see trig identities. So be aware of that. So I now know the tension is 1803. I'm going to come back over here, 1803 cosine of theta t, which is 25, which is times cosine 25, 1634 newtons. And then putting that in here as well, newtons, plug in please. Sine of 25 degrees plus FPY is equal to 3200. FPY is equal to, in this case, I guessed right because that's going to be a positive number, which is good. 1803 times sine of 25. What? Sine 25 times 1803. Okay, good. Sorry. Little calculator logic problems. And there you go. So I guess right on my directions for FPY and FPX. And I know what the tension is, and I've solved the problem. And so you have some angled beam problems for yourself to try now.